go find the tablet. Okay. There we go. Should be connecting. Yay, we got everything back. Cool. All right, the recorder is on, and it is time already, so we'll go ahead and continue. So at this point, we have 4 things on stack. We got the unknown thing that is on stack that's represented by a question mark. We got the 4, the 3, and the stack pointer is now pointing to the 2 on stack. So we got 4 bytes on stack that are currently in use. So the next one, we kind of know what it is about. Okay, so we'll take a look at these instructions here, from here to here. What do you think those instructions are for? We are, huh? Oh. Oh, I just erased it. For some reason. There we go. There we go. Okay, so what do you think these instructions are for?
Function call.
It's, huh?
A call.
It's a call. Very good. Okay, so we are saving the return address on stack, and then we transfer or continue execution at the subroutine. Okay, so that means by the time we get here, oops, by the time we get here, we would have the question mark, the 4, the 3, the 2, and then the return address is pointed to by the stack pointer. Is that okay? So that's what the stack would look like when we call the subroutine. Now, when we analyze the subroutine, we know that it has 2 parameters, right?
2 and 3.
That would just be 2 and 3, exactly. So 2 and 3 are the parameters to sub1, okay? So by the time we return, okay, these 2 are really just for cleaning up the parameters. So I'm gonna write it here. So it's just clean up the space used up by the parameters. Okay, so they're not typically very exciting. Okay, but here we have something that is kind of interesting because we are decrementing the stack pointer, which means we are allocating a byte on the stack, and we are pushing register A on the stack. What is the significance of register A after a function call?
Return value.
It's the return value. Very good. Good job. So what we end up here now, on the stack, is a question mark still there. 4 is still there. 3 and 2 are gone because we just popped those. Okay.
Oh, I see. So like the nested calls, like.
Yep. So this is the return value.
Do another subtraction.
Yep. This is the return value of calling sub1 with 2, 3 as parameters. And the stack pointer right now is pointing here. Is that okay? It's very similar to one of your homework assignments, but this is basically just kind of reverse. I give you the assembly code, and we go through the assembly code to understand what is going on the stack, so that we can understand, how we are calling the subroutine. Okay. And then we do, this whole bunch of stuff, which is another call. Okay. So with this call here, okay, the stack is going to look like question mark 4, and then I'm just going to say return value, as a short way to describe this whole thing. So this entire thing is here. Oh, wait.
Oh, it's pointing to return address.
Yep. So I have to erase all that. Okay. So we have the return value, and then we have the return address. And the stack pointer is pointing to the return address when we continue execution in sub1. So this time when we call sub1, the parameters will be, the first parameter is the return value of the nested call to sub1, and then the second parameter is, well, just the 4 that we set up way earlier. Is that okay? All right, so that means with this call, by the time we get back here, okay, this is just cleaning up. So this is just for, oops, I clicked the button accidentally. So we are just cleaning up the parameters. So after this, we will get the question mark, the 4.
No,
the 4 is gone, right? We only got the question mark left.
Return value 2.
No, that's gone too. Because this is param 1. From the callee's perspective, this is param 1, and this is param 2. So the to increment would have cleared these two. The return address itself is cleared by the subroutine. So the caller only has to clear the parameters. Is that okay? But more importantly, what is in A? A is now the result of calling sub with 4, and then the second parameter is sub1 with, oops, I take it back. I got this wrong. Reversed. So we have sub1 as a nested call, 2, 3, and then 4 as the outer, second parameter of the outer call. Are we doing okay so far? Yes?
The end. Right?
And then we store to D. So D is now pointing to the question mark.
Why is it not the other way around?
What? Huh?
Why is it not the other way around?
Because that's how the 4 is pushed way early, right? So when we call sub1 the second time, this is what the stack looks like when we call sub1 the second time, which means param1 of the outer call is the return value of the inner call.
Oh, I see.
So that's why I put the inner call as the first parameter, and then 4 is the one that has the highest address, so it's got to be the second param, and that's why I put 4 as the second param. Okay. So now we're putting, register A, this instruction is storing A back to the kind of unknown thing, so that this so-called unknown thing is now not unknown anymore, but it is now, the result of calling sub1 with a nested call to sub1, 2, 3, and then a 4 as the second parameter of the outer call. So what do you think that seems like in terms of, things that can store values? There are only several things that can store values. We got parameters, we got local variables. There's no heap here. We don't do new or delete in this type of programming. So what do you think this location is corresponding to?
255.
No, but what kind of location is it? Are we dealing with a parameter? Are we dealing with a local variable? Or are we dealing with something that's just temporary, that there's no special purpose?
It gets deleted, so
it's a local variable.
The local variable at the first line in main.
Yep.
Allocating the space for.
Yep, exactly. This is a local variable. So by the time we get to the halt instruction, it's kind of like the return in main, because we don't really do a return here. There's nothing to return to from main. So that means, when you look at this entire thing, okay, I'm going to zoom out a little bit here. So when you look at this whole thing, the first decrement, which is here, is allocating storage for a local variable. So the entire program is now going to look like int. Okay, whether you use int or void with main doesn't really matter, because to us main never returns. Okay, so there's no such thing as a return value of main, because this is not using an operating system. Now, when you have an operating system, the return value of main is actually the exit code of your executable. So when your process is done, okay, when you run your program, it actually does return an exit code to the operating system. A 0 typically indicates there's no problem. I terminate, as usual. Okay, nothing to take care of. A non-zero exit code from a process in Linux typically identifies there's some issue, you might want to report this or do something about it. Okay, but in this case, our toy processor has no operating system, so there's no such thing as return. So if you want to use void as a return type of main, that's fine. Okay, no problem. But the key concept here is that we do have an integer as a local variable, and then x is getting sub1, 2, 3, 4, and that's the entire main. So are we doing okay so far with this, or do we want to spend a little bit more time on this one? This is okay? All right, cool. If someone reminds me, I can export this back into a PDF and push it back onto the web. So so you can use it for study guide or whatever. Is that okay? Sure. Go ahead.
So when you're allocating for a local variable, is it always common just to see at the beginning of the program, or could it be like midway in the program and you're creating it then?
I tend not to use a local variable within a local scope like open brace and close brace, so it'll be usually at the very beginning. Yep. All right, so this is it for this question. So I'm going to move on if there are no questions. Is that good? Okay, looks that way. So we're going to move on to question number 3. Question number 3 is really easy to answer, especially if you make that table of microcode that we were just talking about earlier. So question number 3 is saying, okay, many quote-unquote not so pure RISC architectures have opcodes to perform the following operation in pseudo-C notation. All right, so what we want to do is to look at these two operations kind of closer and say, okay, do we recognize these things? Okay, what is this? This is decrement D. We're just decreasing D by 1. The next one is to store X into D. Okay, looks like we have individual opcodes to do this already. Is that okay? So now we read the question. We read the rest of the question. Assuming the opcode pattern is 0B, which means it's a binary number, 001000XX, XX identifies the register that we are storing to where the stack pointer points to. Figure out the start location of the opcode in microcode ROM and specify the bit fields of each microcode slice. Okay, so I'm reading this part of the instruction. So now it says if a field, oh, this is kind of cool. I can use the scroll on the mouse and scroll on the other side. In other words, I have remote control from this side. Cool. So if a field depends on X, specify X. If a field can be 0 or 1, specify a question mark. If a 0 means a field must be a 0, a 1 means a field must be a 1. Okay, so I answered this question already, and so I can. Unfortunately, you guys won't see the process of answering the question. The start location is not just 2, 0. It is 2, 0 plus X, and then the whole thing shifted to the left by 4. Because I'm looking at the location in ROM where the first slice of the opcode goes, or the first slice of the microcode goes. And that has to be shifted by 4. Why are we shifting by 4? The start location in ROM. Okay, so this has to do with the processor, or the architecture of the processor. Let me do another history and restart Java to look at the processor architecture again. Okay, so when we look at this, and we look at the ROM itself, and we focus on the address bus. The address bus is controlled by microcode pointers. Microcode pointer, as you can see, has 3 hexadecimal digits, which is telling you, oh, okay, it is 12-bit wide and not 8-bit wide. And the reason why it's 12-bit wide and not 8-bit wide had to do with this merger here. This particular merger is taking the instruction from the instruction register, which is only 8-bit wide. But the merger is also having 4 zeros as the least significant bits. So that's why by the time we update the microcode pointer, the least significant 4 bits are all zeros, and then the most significant 8 bits is the actual opcode of the instruction. And that is why the answer to the question, okay, let me see which, this is the tab. So that's why okay, I got it on my tablet actually. So that's why, when we look at the start location, it is 2, 0. The 2, 0 comes from the bit pattern. Okay, it comes from, okay, so it comes from this part. This is the 2, and this is the 0. So 00XX, basically says the least significant 2 bits specifies which register. But the base code is 2, 0. So that's how we got the 2, 0 plus X. So the XX is why we have this X here. Is that okay? So this specifies, not only the start location of one single opcode, it specifies the start location of the entire family of opcodes, where X can be 0, 1, 2, or 3. Okay? So when we look down the slices, it is a copy and paste. Slice 0 is basically, copying decrement D, and slice 1 is copying STDX. That's what we're copying. But a straight copy is not going to get full points because a straight copy would not have the question marks. So you have to identify, okay, what is a don't care? Okay, it can be a question mark, it can be anything. The reason why there's a question mark here is because PC enable is a 0. When PC enable is a 0, the program counter cannot be updated. If the program counter is not updating, how you control the mechanism of specifying, update based on this value or that value, it doesn't matter. It doesn't matter how PC mux is set up. Program counter is not changing. So that's why PC enable is a 0, and then PC mux is a question mark. Address mux in the first one is also a question mark because the first slice is only doing a decrement D. Does that need access to RAM? No. If we are not using RAM, who cares who is driving the address bus? Because the RAM is not paying attention to the address bus. So it doesn't matter who is driving the address bus, and that's why we have a question mark here. Are we using the ALU to decrement? Yep. Okay. So ALU enable is a 1, and OP being 1 means we are subtracting. OP being 0 means we are adding. How do we know all that stuff? It is inside the schematic of the ALU. So for that, you have to go to LogicSim, go to the ALU, right click, and just view ALU. And this particular diagram will show you everything that you need to know about how the ALU operates. So this is another schematic that you might want to print out and bring with you. Okay. The register bank, I'm not really too concerned, personally, but if you want to print it out, it's a small one, so bring it with you too. But this is one that is kind of useful because it tells you how the flags are set, okay? Under what condition is the Z flag going to be a 1? Okay, look it up, it's here, it is fully spelled out, okay? When is the overflow flag going to be a 1? Is it changed when we do a shift operation? Look it up, it is here. Is that okay? So that's why this particular schematic is kind of important too. I would print this out and just bring it with you. Okay, if you don't need it, it's okay. And just in case you need it, it is there. Are we doing okay so far? And once you print it out, you can also annotate with your own writing, which I think is going to be the most valuable part of doing this exercise. It's not just that you have that piece of paper that you might need, but also when you're studying, you're annotating that whole thing with your own notes. And that is a part of studying already. Okay, all right, so getting back to the question. So for the rest of this, our register output 1 select is a 0, is a question mark, excuse me, is a question mark, because this operation does not utilize register output 1 from the register bank. That's the whole idea, okay? We are decrementing, which means we're supplying a 0, 1 constant to the second input of the ALU, which normally comes from register output 1. So it doesn't really matter, what register you select as register output 1 because we are not using it. Register output 0, on the other hand, is important because we have to make sure that we select register D. That's what this 3 is about, because the instruction specifies exactly which register we are decrementing. It has to be register D, and so that's why it is 3 here. And also we are updating it also here, so that's why we have these 3, because these 2 3s are basically corresponding to register D. Uh-oh. Wrong tool. Okay, so this is register D, and this is also specifying register D. RIEN, register input enable, specifies that yes, we are going to change one of the registers in the register bank, so RIEN is a 1. So this is what you need to kind of go through, so and not just really copy the values from the table, because you have to identify which one can be a 1, can be a 0, it is really a don't care, and which one has to be a 0, which one has to be a 1, and occasionally you have ones that has to be a 3 or 2, something like that. So are there any questions about this answer? Do you want me to explain the second slice, or just, this is cool, we're fine?
What are slices that the blank slices for, like 3, 4, 5?
It's just giving you extra space in case you feel like using it.
So,
Yep.
RO1 select, second slice it selects 3 register D before updating
Yep.
to X.
Yep, this is register D again. This one here, that's register D. Because we are using register D, this D here needs to go here.
So, and then X corresponds to C in this case.
Huh? The 2?
Yeah.
Oh, no. The 2 is different, okay? So this is why you need to print out that picture, because you need to find out what is R, register output 0 demux.
Oh, it goes 2 into the
Right, it goes to the demux, so you have to go back to this picture, find out where the tunnel is, register output, which one again?
DMX.
0 demux. So we are looking at this one here. This is controlling the output of this particular demux, and we
Second
need it
goes
to be
to
set
alien.
to 2 because we want it to drive the address bus. So when this is 2, okay, when register output 0 demux is 2, register output 0, which is register D, is connected here. That connects straight to the data port. Okay, so this is the register that is being stored. So, okay, I take it back. So that's why register output 0 select is X. So when we go back to here, so this X here, this X here is coming from this X. Which register are we using to update that location in memory? Now register output 1, on the other hand, is driving the address bus, so it's specifying which location should be updated. So when you look at register output 1, which is this one here, we're using 0. So the demux is using 0, which means this particular demux is sending the output here. That output goes through another multiplexer, which eventually connects to the address port of RAM. So is that okay? All right. So that's basically how we study, quote unquote, study for this test, is basically just make sure that we understand the existing instructions, go through the slices of microcode of existing instructions. Now, you don't have to go through every single one of those, okay? If you go through JCI, I wouldn't go through the variants of JCI, which is JZI, JSI, JOI, and JLI, because they're all about the same. It is just looking at the different flag to determine what to do. If you look up JMP A, I wouldn't look up JMP B, C, or D, because they're about the same. They're just changing which register we're dealing with. So we have families of instructions where if you look up one, the other ones are very similar. Add, subtract, right shift, or and, they're all about the same. It's just, which path are we going through inside the ALU that changes, okay? So there are not really that many instructions that you really have to go through and go like, okay, let's go step by step, slice by slice, bit by bit, and figure out what it does. Okay? All right. So getting back to the question, are there any questions about this one? About this question number 3? No questions? Yep.
Will you have you upcode the pattern starting in binary, and then is it gonna be translated where it starts, or we have to do that ourselves?
If I tell you what the pattern is, then you translate that into hexadecimal. and then shift it to the left by 4 bits. But then you also have to figure out where the register is specified, because in this case it's the least significant 2 bits, but it may not be the least significant 2 bits sometimes, so you have to understand that part. Okay. So that's question number 3, and I think question number 4 is the one that I really want to go over. Nope, not this one. Question number 5 then. We can go back to question number 4 later on, but question number 5 is is one that I really want to go over. This is once again, converting. It's decompiling, which means you're looking at the assembly code, and we want to reverse it back to the C code. This is one that I'm pretty sure we have talked about already, but since I do not have the comments here, and I do not use names for L1 and L2, like if, then, else, and if, that sort of thing. So we basically have to look at this fresh and say, okay, we haven't seen this particular subroutine before. Let's go analyze it. Is that okay? Okay. So we'll start analyzing, and we go straight to the end, because remember, we want to do all the easiest stuff first, okay? Get some partial credit. So we look at these 3 instructions and go like, yep, we know what that is. Okay, this is just return to caller. Got some partial credit, just like that. But we also know that we have a return value of some kind. Okay, oops, I just clicked the button accidentally. So we also know that we have some kind of return value from this subroutine, because right before I return to the caller, I put something into register A. Okay, I don't know exactly what it is, okay, at this point, but I know I put something there. So I know there's a return value. We'll come back when we have time to figure out what it is. And now we go back to the beginning. And one thing that is guaranteed is register D always points to the return address at the entry point of a subroutine, which also means at this point, A is pointing to the return address. After we increment A points to the first parameter. I don't know exactly what it is. I'm just going to call it param1. Okay? And then now B is param1, because we dereference A and then we put it into B. A is the address of param1, but B is the actual value of param1. After this, we increment A again, so it would appear that we have a second parameter of some kind, and C is now the second parameter, the value of the parameter. So are we doing okay so far with these 5 lines at the very beginning of this whole thing? So now we see at L1. Have we seen a JMPI to L1 up to this point of the first 5 instructions?
No.
That tells me we have a loop. Because we are not doing a future jump, this L1 is going to be a backward jump. Okay? Now, it is possible that I might just throw in a label for no particular reason. Okay? But that's not the case here. Okay? Because so we kind of know this is a loop. And we know the structure of the loop too. Because we can see there's a JMPI to L1 from here to here. Okay, and it's not conditional. We always go from JMPI L1 back to the label of L1. Just that by itself tells me this is a while loop, because a do while loop has a conditional branch to the beginning, not an unconditional branch back to the beginning. Okay, and then we also see a conditional branch to L2, which is right after the JMPI, the unconditional branch instruction. This really confirms that this is a while loop. Okay? Okay, cool. So now that we know it's a while loop, we just need to know what kind of condition is it testing. Okay, so we say this is a while loop and it has some kind of condition. Okay. So the condition is based on what we're comparing. So let's see what we're comparing here. We are loading whatever C points to into A. Okay, so we'll do a little bit of analysis here. So A is now whatever param1 points to. Oh, param2, take it back. Is that okay? Because from earlier we know that C has the value of param2, and right now I'm dereferencing C as a result, and I'm dereferencing it and storing it into A. So register A is whatever param2 points to. And then we do not have a compare yet. Okay, the second one, which is this one here, is saying, oh, store that thing to whatever param1 is pointing to. Is that okay? Because this register A is just a bridge between these two instructions. I'm reading from what C points to and then storing that to what B points to. So when you combine these two, it becomes param1 stores, or whatever param1 points to stores whatever param2 points to. Is that okay? All right, that's not a comparison. So now we have this instruction here, which is not going to be useful anymore at this point because we borrowed the AND instruction for other purposes. Okay, but what this is going to do is really testing against 0. So we are really just asking, is register A 0 or not? Okay. Okay, test for 0. And then this instruction here is basically saying if A is 0, go to label L2, exit the loop. Okay. So when you look at all of this, we stay in the loop as long as A is non-zero, because we only exit when A is 0. So when you look at the while loop, it really is just saying this. Param1 equals single equal, not double. Param2. Stay in the loop. And then when we're in the loop, this is just incrementing B, which is incrementing param1. That is incrementing param2. And that's it. That's the entire loop. So to clean this up a little bit, the loop inside, okay, so I'm gonna, okay, I'm just gonna change the color to identify which part are the C code. This is C code, this is C code, this is C code. I'm just gonna open curly brace here and then put a close curly brace here. So the C code is really just saying while dereference param1 equals dereference param2, increment param1, increment param2. That's the entire loop. Is that okay? So we are almost done here. We're almost done. We just have that last little bit of stuff here. So this one is saying A points to the return address. We increment it, so the A now points to the first param1. And so the return value is really saying that A is param1, not pointing to, but is actually param1, because A was pointing to param1, but we dereference it. So that A is actually param1. So my return instruction, so when you look at all of this stuff here, all of this is specifying let's return, but not just return to the caller, but we also specify the return value is just param1. Okay. So we got two parameters. What do you think of these parameters in terms of the type? Are they integers? Are they pointer to integers? Or what? What do you think? I mean, just look at the C code. Don't even bother to look at the assembly code at this point. Look at the C code.
They should be pointers.
They should be pointers. Very good. Because we see that we are actually dereferencing param1 and param2. So from the use of the parameters, we know that they are pointers. Okay? What they point to can be signed or unsigned. There's no indication whether they're signed or unsigned, because the only thing that we did with what they point to is to test for 0. Okay, we didn't compare. We did not compare for less than, and therefore we are not seeing any JCI or JLI instructions. And without those, I cannot really tell whether it's signed or unsigned. I can only say that, okay, some kind of pointer to integers. So now when we go back to the prototype, now we can say, oh, what is it returning? It's returning param1. So the return value has the same type as param1 itself, okay, which is also a pointer. So now we can now say, okay, we can just use integer or unsigned, it doesn't matter which one. It is returning a reference to a pointer to an integer, and here is sub1. It has got in param1 being a pointer, and param2 is also a pointer. And going to use an open curly brace here to begin the entire function, and then go here and close the entire function with a closed curly brace. So that would be the way to work out this particular question. And if you document your answer this way, perfect. I get to see how you reason it out. I get to see, how you, say, oh, okay, this bunch of stuff grouped into this smaller block. This smaller block is a part of a larger block, and that larger block is actually doing this in C. So I prefer that you document everything like this, which also means sometimes you may need an extra sheet of paper if you kind of like mess up, or if you want to start from scratch. I will bring some extra questions just in case, but I may not bring enough. So you might want to bring extra pieces of paper just so that you have the extra space and go like, okay, scratch that, I'm going to continue over here. But is the process okay? Does everybody understand the process of doing this and what you need to understand in order to answer the questions like these? Now, we have worked on quite a few programs already, okay, translating from C to assembly, and many of those are uploaded. Some of those are uploaded. They're all recorded for sure. So what you can do is to go through those programs, get rid of all the comments, okay? Let it sit for a day, because if you just do it right away, you can remember the C code. So let it sit for a day, and then come back and then start to work on it. Or if you have a study buddy, it's even better. So you would strip the C code or the comment for one particular, say it's program 1. Your buddy will strip it for program 2, and then your buddy will give you the stripped version of program 2. You give your buddy the stripped version of program 1. Then you guys both can do the exercise, and then a few hours later, exchange. So that's one way you can study for this test, is to go through the code that we have already talked about, especially the recursive ones. Okay, the recursive ones are kind of, and also not so interesting. So what do you think? Do you guys think recursion is confusing, interesting, or do you think, I'm hoping that you guys would go meh, okay? Because recursion is no different. It is the same mechanism as calling any other subroutine. Okay, calling the subroutine that you're currently in doesn't change how we call or how we return. It's exactly the same mechanism. Okay, so I'm hoping this also helps to demystify, the concept of recursion from your other classes. Because when I was first introduced to recursion, it was in CIS, what is equivalent to cisp310 here, okay? And I go like, I look at the program, I understood the concept of, okay, there's a local, this is a local variable, but it was not explained very well that there's one local variable per invocation. That was never really explained to me. So it always looks kind of mysterious. It's like, there's only one X here, but I'm calling the subroutine over and over again. How come X is not clobbered? It's until I took assembly programming, back in those days, then I go like, oh, now everything is clear. There's one here on the stack, 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 but each invocation can only access its own X, so all of the other ones are out of reach. They're on the stack somewhere, but I'm not touching those. I cannot touch those at the time. So that was really helpful to me. So now that we are done with this one, we can see there's an Another question? Nope. Okay, so we can go back to the previous one, which is question number 4. So question number 4 is recursive. Okay, and I can zoom in just a little bit here. So question number 4 is recursive, because we have a recursive call. Do you guys want to do this, or do you think, we can do this? Do we want to do it? Yeah. Okay. All right. So for this one, I'm just gonna use a notepad because I can type a lot faster than I can write, and you don't want to deal with my penmanship either, unless it is necessary. The other one, I kind of really like the idea of using a tablet because I get to kind of do things in a much more free form way. But with this one, it's not really necessary, so I can just do it with a notepad. Okay. So to implement this, we start with sub 1, and we want to make sure that k is on top, n is below that, and then return address is before that, and register D is pointing to that one. Okay. You don't have to do this, but I like to have a visual picture of what is on the stack at the entry point of a subroutine so that I can keep track of stuff. Okay. Okay, so what we need to do is we need to compare k with 0 and n with 0. Okay. And you cannot change the order because this, in C and C++ and most other programming languages, when you have a logical operator like AND or, it has to evaluate from left to right. And it has to use short-circuited evaluation, which means if the first comparison gives you a definitive answer of the entire expression, you don't bother with the second. Okay.
Oh, I see.
So now we need to get k, so we need to do a CPR CD, and I just personally like to comment that C is now pointing to the return address, just like D, because it's a copy. Increment C, so now C points to the first parameter, which is n, but that's not what I need at this point. So I increment it one more time, so the C now points to k. Okay, I don't need the address of k, I need the value of k. So I need to use an LD instruction, put it into one of the other registers. I want to keep C around the way it is. So A is now K. And then we do LDIB 0, so that B is 0. And now we can do a comparison. We're only comparing for equality, which means the order of the compare doesn't really matter. So CMPAB is fine, CMPBA is fine too. Huh? And then we have a JZI. Now this time you have to be careful where you are branching to, because the JZI is not branching to the else, it is branching to the then, because this is confirmation that k is in fact 0, so we should go to the then branch. Okay, so you have to be careful with this one because we are going to the then branch, which is going to be here. Okay, so let's say that is non-zero. Okay, we have a second chance. We can now test n. So we can say decrement C, because C was pointing to k, decrementing it back, it will point back to n. So C now points to n. LD, I can reuse the same register, that's fine. I can reuse register A, so that A is now n.
And B still has 0. So
B still has 0, so we can just compare AB. And then we have another JZI to then, okay? So what it means if I get here is the else. So you get a choice to implement this. You can move the entire else branch to where the working cursor is. That's fine. You can do a JMPI to the else label so that the ordering of the C code and the assembly code would be the same. So that part is up to you, okay? You get to choose how you want to do it. I'm just going to waste an instruction here to go to else so that I can preserve the ordering of the blocks of code, okay? Because the then block is occurring before the else block. So this one is just specifying a return value of 0. So LDI A with 0 will do it. We can then go to JMPI to the end of the conditional statement. So we have an end if all the way down here. And now we have the else block. So the else block is kind of the interesting one because it is the recursive call. Okay, it's trying to implement this part here. And I can make this up, get this up a little bit so that people in the back can see it. Because otherwise, you may not be able to see past the head of other people. And I can move the entire thing up a little bit that way too. Okay. So now we have to implement this whole thing, okay, which is we need to go find k first. So you might say we got that stuff in C also, okay. Well, that is the case, okay. But keeping track of what C has throughout the execution can be very kind of cumbersome, and you don't want to make a mistake. So you can always just kind of copy again. There's no point deducted for a program that is not as efficient as it possibly can. Okay, so we can always just reload it. Okay, so we need to get to k, and k is the second parameter, which means I need to increment C twice. So the C points to k, and then we do a LD AC, so the A is k. And I'm going to do a little trick here. I'm going to reserve a byte on the stack and do a store. In other words, I'm just pushing k on the stack. Push k on stack, and then I'll do it one more time. Decrement D, STD A. So we push k twice on the stack. The reason why I'm doing this is because when I'm done with the nested subroutine call, I don't want to go through all this trouble to calculate k again. Since I got k already, I'm going to push a copy of k on the stack so that when I return from the subroutine, I can just pop the other one from the stack, and I got k back. Okay. You don't have to do it this way. Okay. You can always just do the call, the recursive call. When it comes back, do all the calculations again. That's fine. Not a problem. But I'm just going to be a little bit lazy here. Okay. Next, we need to push n minus 1. So since C is still pointing to k, we can now decrement D, C, so that C points to n, and then we do a LD, and I can reuse A at this point, so we can do this. A is now n, decrement A, so that A is n minus 1, and then we decrement D, STDA, that's pushing n minus 1. So we now have k on the stack, we got n minus 1 on the stack, it is time to make the call. So that's LDIA with sub1 return address 1. There's only one, so whether it has a 1 or not doesn't really matter. And then we push that on the stack too. STDA, push return address, and after that we have to remember to do unconditional branch back to sub1, because that's how we make a call. After the call returns, we always have to increment D to clear all the parameters. There are 2 on the stack. Okay, if you do not do the increment, you are not just wasting space on the stack, but the stack pointer will not be pointing back to the return address at the end of the subroutine, and as a result, the subroutine will not return correctly. So these 2 increments are not really just to, oh, we're just being nice and conserve your memory. Nope, these are needed in order to return correctly. Yep, go ahead.
Don't you still have 2 copies of k, so would that have...
Yep, we still have a copy of k, but we have not cleared that yet. In fact, right after the second increment, this is where we get it back. We do LD, AD, okay, pop k to register A. Now we increment.
Oh,
okay. So now we have, oh, wait, there's a problem here. I cannot use A, because register A has the return value of the recursive call, which I need to keep around, right? Because register A has, okay, this is really cool because I can do it on both sides. Okay, so register A has this. And that's why I cannot reuse register A. I have to say, oh, okay, let's not touch register A. So that's why I'm putting K, I'm popping K back to register B. Okay, so now we can just say, oh, okay, that's really convenient because the return value is the sum of these 2. and one of them is in A already. Cool. So just add AB, will compute the return value. Okay. This is the return value. We got it done, and now we can just merge the branches to end if. So end if doesn't need to specify the return value anymore because each branch is specifying the return value. Now at the end if, we just need to continue execution in the caller, which means we just have to do LD B D pop return address into register B. Don't forget to increment D first after that, and then we have a JMPB to return to caller, and that's it. Is that okay? Sure.
Oh, and if you have multiple recursion calls, sub return address 1 gets updated to return address 2 and
Yep.
so on.
Yep. Yep, but it's the same mechanism. Every time you call, you have to know where the subroutine is supposed to continue execution, and that's why you need that label. All right. So are there any questions about all the material that we have talked about today? Including the stuff that we talked about in the lecture, which is the architecture itself and how the microcode works. No questions? What about, what kind of material you might want to bring to the test? Because it's open book, open notes. That's one big flexibility right there for you guys to say, okay, I might need this, I might need that. So are there any questions about that part?
What would you bring to the test?
What would I bring?
The list.
Oh, I would bring, for sure. Okay. That's a smart question. Okay, so even though I came up with all of this material, my memory is very bad. Okay, you just asked me what I said two sentences ago. I cannot remember. So I need a lot of backup material, to have all the details, right? So the stuff that I would bring would be the schematic, which is kind of like the logic sim diagram, schematics of the processor, the main processor. I would definitely bring one for the ALU2. So those two I would definitely bring. The register bank, I'm not really concerned about, but if you want to bring it, that's good too, okay? So I would put it in parentheses. Okay, maybe that, okay? I don't think it's going to be too helpful, but I will bring that too. I would bring a table of microcode implementation of opcodes, okay? So that's what we were talking about earlier in the lecture. You can do this, using the source code that I provided in the opcodes, folder, which requires a little bit of programming, and you need to understand my code a little bit to kind of make that happen. If you don't want to spend the time to do that, you can always do it manually, which I kind of started and kind of illustrate a few steps. It's not too bad, especially if you work with another student. If you have a study group, you just say, okay, let's divide all the instructions into 4 groups, okay? Each person is going to deal with 3 or 4 instructions. Before you know it, it's done. Okay, the question is, can you trust the other 3 people in your group? Okay, so that I would bring. I would bring, possibly, okay? I would bring example code, okay? And I would definitely bring both the C and the assembly version. Okay, I would find as much sample code as possible that has both the C code and also the assembly code, because this way I can, in a test, if I say, okay, I don't remember how to do this, then I can say, oh, okay, how was that done in a sample program? This C code translates to that assembly code. Ah, okay, got it. Okay, or when you have to deal with a disassembly program, disassembly question, it's the other way around. Okay, how do I recognize that this is that in C? You now have sample programs to help you. Okay. I would bring a calculator is not going to be helpful. Okay, I don't think it's going to be helpful. But if you want to bring one, that's fine. I don't think it's going to be really helpful because the kind of conversion that we do, which is in hexadecimal, is just a table lookup. Okay, so it's not going to be very helpful. We won't have floating point number stuff in this test, so there's really nothing that has values to compute in this particular test. So I'm not really too concerned about that. I would bring scratch paper, and I would bring the ones that have grids, because this way it's easier to keep track of what is on the stack. Okay, because a main part of what we're doing with writing subroutines and the caller and stuff like that is to have a really good idea of what is on the stack, what the stack point is pointing to, what this register is pointing to, and so on and so forth. And having grid really helps to line things up so that you don't accidentally go count the wrong thing. So I would bring scratch paper that is gridded, that has grids. So that would be kind of like my minimum thing to bring. The table of opcode microcode implementation is really kind of important because I definitely want to know how the microcode would interact with the processor schematic. So between this and this, I have all the actual details that I need. Okay, the rest is really just so that I can cross-reference things that we have done in class, but I cannot remember exactly how we did it. Okay, now we can just kind of look it up. You can bring my solution to all the homework assignments. Okay, anything that is printed or handwritten prior to the test, you can do it. Well, except for the exam 2 questions itself. But nobody's going to get an early copy of that, not even me. So are there any other questions? That was a good question. Who asked that question? Okay, that was a good question. What would I bring to the test? But just because this works well with me doesn't mean that it will work well with you. So you can use it as a starting point, but you might want to add additional stuff to it. Okay. Yep.
Could you upload the annotated version of the
Oh,
practice,
yeah. I can do that.
And the code that you typed out?
You mean this one?
Yeah.
Sure. Let me.
That'd be a good example code.
Okay. Yeah, I would agree. And this is which question? I think it's question number 4. So this is spring 17 final exam question 4.ttpasm. Okay, and I'll upload this right away before I forget. Okay, is that the right course? Yep. Okay. And let's see, where should I put it?
Put it in the folder.
Yeah, I think it's better to put it in the folder. Yeah, this is the right place. Okay, so we'll put it here. So we'll upload the file. There we go. Okay. The other one is on my tablet. So can I switch back to the tablet so you can see? You guys can see how we can do this. Okay, so we can go back out. And this is all in. This is in the test, so we have, I think it's in this folder. Yep, okay. So let's see what we can do here.
There's an export to PDF.
We can export to PDF, okay. And then we can view it. Where is it putting it? That's the question. How do I save it?
Maybe the drive PDF viewer.
Okay.
And then upload it to drive. Top right.
There we go. So we'll upload it to cisp310 shared. final exam answers. Select. And answered. That's good. Then save. All right. So there's that. Do you want me to upload the processor thing, after I do the annotation? I don't think that's going to be very helpful. There were only a few things that I did. Yeah, I don't think that one's going to be very helpful, but it's here. We're talking about this one, where most of the annotation is up here. No? Okay. All right, cool.
What are we doing Thursday?
Sorry?
What are we doing Thursday?
On Thursday, we can move on to new topics, or if people have questions to ask related to the test, we can do that too. So the pace of this semester is a little bit different from last semester, so you can see how the topics are shifted a little bit. Any other questions? No other questions? All right. So go ahead and study, as early as possible, so that if you, encounter any questions, by Thursday, you can ask those questions in class. I would definitely try to study, some, at least to the point of, on Thursday you might have identified, okay, I need a clarification of this, okay? Then you can ask those questions. All right. Anything else? All right, so the exam date is set to next Tuesday, and we're gonna use the lecture time only for the test. So we have 80 minutes for the test. You just need to make sure that you kind of pace yourself, look at the point values. More likely than not, I'm gonna have questions of exactly the same point values. So then you just need to pick the easiest, okay? Pick the easiest one, work on it until if you're stuck, fine, move on to the next one. You guys know the strategies, right, already. Okay, don't get stuck or too stubborn with one particular question. Use your time and go like, okay, there are 5 questions, 80 minutes, so it's good to give yourself maybe 12 to 15 minutes per question. After 15 minutes, even if you're kind of hot on the trail, just move on to the next one. Okay, because the next one may be easier. You can get points, faster that way. All right. Any other issues, concerns, questions? All right. Okay. And I might give you guys some, ungraded assignment, also just to practice. Okay. But there's quite a bit of practice already. I think the way it is, I can dig up some more exams if I can find some. The problem is I changed the architecture between semesters, so some of the older questions that do not apply anymore. So that's the reason why we only have a limited number of questions for this class. Okay, so I'll see you guys on Thursday.
Yep.
Have a good lunch today.